Thank you. Okay.
Okay, so thanks for being there, and thank you, Mr. Gielen, to accepted our invitation. Mr. Gielen is a full professor at the Department of Electrical Engineering at Gielen in Belgium. He has made his whole career is in Gielen, and he had his PhD in 1998 Gielen in Belgium. He's making the research topic is on CMOS analog and mixed signals circuits, and he's also working on design tools and simulation tools, and also testing circuits. So Mr. Gielen will make a presentation on designing analog function without analog circuits. Mr. Gielen, for his use. Thanks.
Merci beaucoup. Bonjour tout le monde. Je suis très honoré d'être invité ici pour parler de notre recherche dans le domaine des circuits analogiques. Mon français n'est pas parfait, donc je vais donner la présentation en anglais, si ça vous convient. And I will speak slowly so that everybody can follow the presentation. As said, I'm a professor at the KU Leuven. C'est un mot difficile pour Rémi, mais Leuven refers to the city where my university is located. And the presentation is about how to design analog functionality, but without using actual analog circuits, which means by using digital circuits. Now, if you have any questions, you can type them in the chat or leave them to the end for the Q&A part at the end of this presentation. This is the abstract, but an important start is just to illustrate for those of you who don't know exactly where Leuven is. I think you all know it's somewhere in Belgium, but we are here just east of Brussels, so à l'est de Bruxelles. And you are here, and so you see it's a lot more to the south, so probably a lot more warmer than it is here today, at least. But the distance is not that far. Now, Leuven is a special city in Belgium, and that you can see from these pictures. So here are some snapshots from the city center. This is the old city hall and some old buildings dating back to the medieval times, the Middle Ages. And here you see the library building of the university. Leuven is a small city. It's not at all comparable to Bordeaux. It only has 100,000 inhabitants. But it's famous for two things, and the first thing is the university. It has a university which is the largest in Belgium. Largest in terms of number of students, and you see here that the total number of students in our university is 56,000. Now, we have a few campuses outside Leuven, so inside Leuven there are about 45,000 students. Now, you can imagine that when you have 45,000 students in a city with a population of 100,000 people, that this has a big impact on the activities and the liveliness of the city. It's really a university town. That means that everywhere in the university you have buildings of the university, and so you have the library here. There are statues everywhere, and this, for instance, is the famous statue that indicates the fountain of wisdom, where you see the student pouring wisdom in his head or her head by reading from a book, a course book, a textbook. But of course, there are other activities that students do, and that is what you see here. And this brings me to the second important thing where Leuven is famous for, and that is the beer. Leuven is the hometown of the beer called Stella Artois. It was brewed here. It's still brewed here in Leuven. And of course, students take a lot of advantage to drink it, especially in the sunny moments in spring and summertime. So I invite you and with your student branch also, that if you ever think of visiting another student branch, why not come to Leuven and interact with the people here, the students here, and have an exchange in some sort. It's certainly recommended. But back to the talk. One of the strengths of our university is in electronics, micro and nano electronics. And so I'm in the Department of Electrical Engineering and a professor in analog integrated electronics or mixed signal integrated electronics. And so that's also the content of my presentation. So I will give a brief introduction about the importance of these analog electronics in today's smart world. And then I will explain how we can make analog circuits small, how we can make them robust, and how we can make them smart. And I will end up with some conclusions. So let me start by saying that today electronics have become ubiquitous in almost any application. Electronics is used in cars, in automotive. It's used everywhere in industry, industrial applications. More and more also in our houses. Home electronics. We use a lot of electronics in the healthcare system. We have all kind of gadgets from smartphones to cameras and so on that are being used, and we use a lot in infrastructure. So all these applications, wherever they are using electronics, and the original motivation to use electronics was that they allowed to build control systems, like for instance in infrastructure or industry, where you want to control how the train is operating or how the machinery is functioning in the company. But today they also use electronics a lot in order to add smartness, to add intelligence to systems which in the past used to be very dumb, just simple control systems. Now, today, they add, through the electronics, they add this intelligence so that the systems kind of behave in an intelligent way. This means that they adapt to the circumstances, that they take actions automatically under certain conditions, and so on. Where do we see this? One example is industry. And so this slide shows you the evolution that we experience in the factory where products are being made, and where originally the industry was with mechanical production powered by steam and water. Later on in the 19th century, this turned into mass production assembly lines with electrical energy and manual labor. Later on, this manual labor was automated with robots. And what we have today is the evolution towards Industry 4.0, where the use of all kind of sensors that are networked and that collect data and that communicate data through the cloud, that this results in an intelligent factory. Other examples are shown here. Robots. There's more and more need to use robots in our society. Today, there was in the news that there is a shortage of people to work in the home care, no, to work in the care facilities for elderly people. So elderly people in Belgium, if you cannot live by your own in your own house, they go to a care facility. Well, there are not enough workers to take care of the people there, and so robots, if made intelligent enough, could be a solution. Of course, in collaboration with humans, with human workers, could be a solution, a substitution for that shortage of human workers. But they could also be used for home delivery of packets that people order today online in all kind of online web stores and all that. Another example is on the right, is the autonomous driving cars, where the whole idea is that the number of accidents that occur by cars or with cars involved is too high. And so by making cars self-driving, making them autonomous, that the number of accidents, hopefully, that is the goal, will go down. Because the autonomously driving cars, which are equipped with all kind of sensors and cameras and all things, radars, lidars, etc., that these cars collect more information from the environment and therefore are better informed about other people on the road, about objects on the road, etc., and therefore that accidents can be avoided much more. So that's an example where the electronics will result in smart systems. Now, in this context, there is a large trend to digitize things. We like to digitize data as much as possible. But the problem is that the data for all these applications that I mentioned, the signals have to come from the physical world. Like I said, the sensor data from a car, the camera images from a car, and so on, and all these data, all these signals, they are analog in nature. Yet, the bulk of the processing of the signals will be done by digital electronics, and that is why the analog circuits are needed as an interface. They are needed as interface between the outside world and the digital core of our electronic systems. So the analog circuits or the mixed signal circuits, mixed analog digital, are the shell, the interface between the cyber world, which is digital, and the analog world, the physical world. And then it's clear that the more digital we want, we also need more analog. So analog will not disappear due to the digitization. Analog is exactly needed because of the digitization. Just an example of such an analog interface chip that we developed for an automotive resistive sensor readout. And so we do a lot of research on these subjects in order to continuously improve the performance of these circuits beyond what you find in your cars commercially. So we do research to improve the performance, to improve the capabilities in our laboratories in Leuven. And we make prototype chips, as you see here. This is an example of a chip photograph. And the whole idea is that the industry then later on picks up these ideas and implements them in their commercial products. And then even a few years more later, the car companies will pick up these chips and use them inside their cars. The whole chip here measures about 1 millimeter in this direction, and about 1.8 or close to 2 millimeter in this direction. And it's an analog to digital converter that has a resolution of 16.1 bits. Now, the sensing is used as interaction with the physical world in order to collect data. But then, of course, the sensor has this data and it has to transmit the data to some place where the processing of the data is done. And often this is in a central server. And for that, the sensor needs to be networked to the internet. And we call that such a setup, we call the Internet of Things. It's an environment where things, objects, like sensors, are connected to the internet through some wireless communication scheme. Of course, we will not hook up every sensor with a wire, so it's a wireless connection. And so this market of IoT or Internet of Things devices is really expected to grow enormously over the next years. So now we are here. And so here you see some data of how the market is expected to grow in the coming years. And the average growth is 15.3%. And this is a lot more than the average growth of the total semiconductor market. And that growth of the total semiconductor market is even a lot bigger than, for instance, the growth of the French national economic product. The gross national product of France in its entirety does not grow with 15.3%. Neither does the one from Belgium. So this means that electronics and certain areas in electronics like IoT are really drivers for the electronic market. Business-wise, the volume was $46 billion in 2019, and it's going to grow to $114 billion in 2025. In euros, this is slightly less than these numbers because the euro is slightly higher valued than the dollar. Okay, so what are the requirements for such sensing applications? Well, first of all, it's clear that they must meet the performance requirements of the application. If you use a sensor in a car, then it's clear that all the automotive strict requirements are needed. But secondly, it's also important that the the sensing devices do not consume too much power. Maybe in a car, this is important, of course, because ultimately the energy comes from the diesel or the gasoline that you take. But it's even more the case in home applications, in medical applications, and so on, where the energy comes from a battery, and so where the power that you consume has an impact on the lifetime of the system. A third requirement is that the solutions must be very reliable and robust. Again, this is very obvious in automotive application or a biomedical application, but also in other situations where you install these sensing devices, these IoT devices, they must run for a very long time under all kind of environmental conditions. And finally, a very important requirement is the cost. For many of these applications, they will only be commercially successful if we can reduce the cost of the IoT solution. Now, cost of a solution depends on the one hand on a fixed engineering cost, but then secondly on the per unit cost for every unit that you fabricate. And the per unit cost for a chip depends a lot on the area of the chip. So low cost solutions means, in this case, low area solutions. And finally, with all these intelligent applications, we also want the solution to be smart. So that being said, how can we make the circuits cheap and therefore small? Well, let's look at a normal sensor readout unit as we encounter them in an IoT device. This box with the cross here represents the sensor. Can be anything. It can be temperature sensor, can be proximity sensor, it can be a radar, whatever. Then the normal steps we do in the analog interface before we do the processing in the digital domain, the normal steps that we do are amplification, filtering, and digitization. So these are the typical analog functions that we use in the interface on the sensing or receive side of things. Now, if we design circuits, and I'm quite sure if you're all electronics students, that you know that these analog circuits, the amplifiers, the filters, and the A to D converters, that they can be quite large in area. And so the question is, what makes them large? Why can't we make the analog circuits small? And for this, we have to go to some basic analysis that has been done by some professors, and that relate the power consumption of a circuit to the frequency range F and the dynamic range dr that is requested. And Professor Eric Fritos, who was a professor in Lausanne, he has derived that because of thermal noise limitations, the power that a circuit needs is proportional to the speed or the bandwidth of the circuit and the dynamic range. And Professor Kinget, who is now professor in Columbia University, but who actually did his research on this subject at our university in Leuven, also found that the power of an analog circuit is proportional to the bandwidth and to the dynamic range in a very similar way, but with a different constant of proportionality due to the mismatch that is present in the circuit. So we have a constraint between the two due to the noise and due to the mismatch. And in both cases, the relationship between power, speed, and dynamic range holds because of the area of the component. So let me explain by illustrating it with the noise. If we want to make the dynamic range of an application larger, and we know that the higher amplitudes are limited by the supply voltage, then we can only increase the dynamic range by making the lower amplitude level that we can process in the application, by making that lower. And if this level is limited by noise, and noise, integrated noise, is given by kT over C, then we can only reduce this level by making the C larger, which means a larger area for the capacitor. Yeah. And so a larger capacitor means a slower circuit unless we keep the bandwidth by increasing the power consumption, increasing the current, therefore the power consumption. So that's why the area is linking the power, the bandwidth, and the dynamic range. And the same is true for the mismatch. If we want to increase the dynamic range, if it is limited by mismatch, then we have to make the mismatch smaller, and that means that we have to make the components larger. So the area is the big thing that links speed, accuracy square, and power, both for noise and for mismatch. Now, if our application has a certain bandwidth, so the speed is constrained by the application. And if the application requires a certain accuracy and our power is limited by the usage of the battery, then it means that we have no flexibility. It means that the area kind of fixed. Of course, things change a bit when the technology changes, so these parameters are technology dependent here. So when we go to another process, things do change a little bit, but essentially the whole thing is fixed, which means that the area is large. So even if we scale the electronics to a CMOS technology node that is more advanced, the analog circuits still kind of remain large, and the power consumption still kind of remains large due to these constraints here. Now I will illustrate this with another design that we have done over the past years, which is a biomedical chip design example intended for neural recording and stimulation, where the whole idea is that we insert a probe into the brain of ultimately a human person. But of course, in the experiments, we don't use human persons, but we use mice or rats. And we record the signals from the neurons, we process them, and we can then, if needed, for persons or animal models that have a physical problem in their brain, we can then stimulate the neurons in order to have the humans and the animals behave normally. We made a chip to do that, and here is the chip photograph. So here you see the probe. It's all done on a wafer, on a silicon wafer. So both the probe and the electronics are all integrated on a silicon wafer. And we then cut out the probe from there. So I will indicate where is the probe. So here is the electronics, which is at the side of the probe. And then here is the probe itself, which when cut out kind of looks like a needle. So it kind of looks like this needle here. And then there are electrodes on this needle where we can either record the signal from the neurons, and for some electrodes, we can stimulate the neurons. And so this shank or needle is about 1 centimeter long by 100 micron wide. So it's a very long thing, about this size, with a very tiny thing. And then the probe area where we have the electronics is about 3 by 3 square millimeter. On this probe here, there is in total 455 electrodes, and we can read out 52 electrodes. So that means that if we zoom out the electronics here, we have 52 parallel readout channels that we multiplex on 13 A to D converters. And in the readout channel, we do this amplification and this filtering. And we can, it's programmable, so we can program what signal we want to read out. On top of this, we have 13 stimulation electrodes where we can steer the neurons and build this closed loop system. Now, the drawback is that we want to increase the number of electrodes that we can read out and stimulate. But for that, we need to make the analog electronics smaller. And like I said, we are limited by the requirements. The requirements in bandwidth of the signal and the requirements in desired accuracy. So that limits the size or the area of the electronics, and therefore that limits the number of channels that we can, or the number of electrodes that we can read out at the same time. And it also limits the power consumption. So at this moment, this solution has a power consumption which is still quite high. It's 17.8 microwatt per channel. So the question is, if this is the standard readout, how can we reduce the area and how can we reduce the power consumption? Well, I told you that as long as you stick to the current paradigm, so the present paradigm being used to represent the signals in a voltage range, then we are stuck with this constraint that links power to speed and to dynamic range square. We are stuck with that. So that means that in order to find a solution, we have to think out of the box and find an alternative paradigm. And the paradigm that we investigated is to not represent the signal as a voltage in a voltage range, but to represent the signal information in the time domain as time domain signals. That means that we need to convert the sensor not to a voltage, which we then digitize, but we convert the sensor information to time frequency information, which we then digitize. Yeah. So the change in paradigm is that the sensor information is converted into time frequency. That's the same. Frequency is 1 over time, or occurrences per time unit. So we convert sensor information to time or frequency and then digitize that without using this voltage range. Why does this look more interesting? Well, because the voltage range in electronic circuits is certainly not increasing, and the supply voltage in more advanced technologies is actually decreasing rather than increasing. So there is very hard to get an improvement on voltage. While the progress in CMOS semiconductor technology is to make transistors always smaller. Depending on the application, maybe some automotive designs are still done in 180 nanometer CMOS, but more advanced designs today are done in 16 or 12 nanometer CMOS, with already some early attempts to use maybe 7 nanometer CMOS technology. So when you use transistors that are always getting smaller, in principle, they should also become faster. And so if the transistors become faster, this also means that the resolution in timing is improving. And so we have, by working in the time domain, we have the advantage that we take advantage, or at least have the potential to take advantage of this continuous improvement in timing resolution. Now the question is, how do we do that? It's easy to say, okay, sensor information converted into time or frequency and then digitize that. The question is how to do that. Well, how can you convert a sensor signal into a time signal or a frequency signal? The way to do that, of course, depends on the type of sensor. So let's take, as an example, a capacitive sensor. For instance, a pressure sensor that measures the pressure by having a capacitor, and the pressure and the plates of the capacitor are movable, and when the pressure on the outside of that capacitor changes, the plate moves, and therefore the capacitance changes. So the capacitance of that sensor is a measure of the pressure. So how can we convert the pressure signal, which is reflected, into the value of the capacitor? How can we convert that into a frequency signal? Well, we can do that by using a ring oscillator. A ring oscillator, as shown here. If we put a ring oscillator, as shown here, as you know, a ring oscillator, due to the feedback, will oscillate continuously at a certain frequency, and this frequency of oscillation is determined by the delay of the stages, by the delay of the inverter stages in this ring. So that means that if we insert our sensor, our capacitive sensor, as a delay, as a load to one of these delay elements, then the capacitor of the sensor becomes a load for this particular inverter stage. Therefore, it will influence the delay of this inverter stage, and therefore it will influence the frequency of oscillation of this ring oscillator. So in this way, the sensor signal, the pressure in this case, in this example, impacts the delay of one inverter stage, and therefore impacts the frequency of oscillation. So in this way, we can convert the sensor signal into a frequency of oscillation of the ring oscillator. Question number 2, how can we then digitize this frequency signal? Well, in order to do that, we use a second ring oscillator that is exactly the same as the first ring oscillator, with the only difference that here we have capacitors which can be switched in or out under digital control. And the digital control comes from here. So the digital control controls the switching in or out of these capacitors. So they are digitally controlled capacitors. Now the two ring oscillators that we have, we put them in a loop controlled by a phase detector. So that means that the output node of this ring oscillator is one input to the phase detector, and the output node of the second oscillator is the second input to this phase detector. The output of the phase detector is this digital signal that controls the capacitors in this ring oscillator. Now, this is a negative feedback loop. And like any negative feedback loops, it tries to make the two inputs, so the normal input and the feedback input, makes them equal. Now, in this case, it's a loop that operates in the phase domain because it's a phase detector, and the phase detector compares the phase difference of the two input signals. Therefore, the feedback loop will make the phase difference between the two signals 0. And when the phase difference is 0, it means that the two oscillators operate at the same frequency. So that means that the digital control signal here, when the loop is in equilibrium, that the digital control signal is such that the capacitance that is switched in here is as close as possible in a digital sense, in a digitized sense, to the sensor capacitance that we try to measure. And therefore, the digital signal at the output of this loop is a digital readout of the physical signal that we measure through the capacitance. And in this example, the digital readout of the entire circuit is a digitized version of the pressure that we measure in the capacitive sensor. So in this way, we have first converted the sensor signal into a frequency, and then in a second step, we have digitized that frequency information towards a digital output. Okay, so that's how this could be done. Now, if we look at this structure, what do we see? Well, first of all, what circuits do I need? Well, this is a ring oscillator, and a ring oscillator consists of inverters. What is an inverter? An inverter is a digital block. So this whole thing is a digital block. This is similar. It's a digital block, and this is a phase detector. It's a digital block. So that means that I do have a circuit that converts a sensor signal directly in a digital output, but I'm only using digital circuits. I'm not using analog circuits. Therefore, the limitations that we had before on the noise and the mismatch in traditional voltage mode analog circuits do not apply here. So it means that this architecture may result in smaller chip areas and therefore cheaper electronics, and also in a solution that is more scalable with technology, because the digital circuits can become smaller when the technology improves. So that's one advantage. A second advantage is that because I'm using one oscillator and a second oscillator that is identical, if the two match well enough, then any errors, any deviations that are common mode, for instance, temperature changes, will affect the two oscillators in the same way. So that means that any common mode variations, the circuit will be insensitive to those to first order. And a final benefit is that if you look at the structure carefully, and we know that the relationship between the phase of a signal, of an oscillating signal, and the frequency of the oscillating signal, that relationship is an integration, then it means that we have here a loop where I take the difference between two signals and where I also do an integration, which mathematically can also be written as a summation, which means that I actually have a delta sigma modulator here, a delta sigma modulator, be it not in the voltage domain, but in the phase domain. Okay. Now, if I have a delta sigma modulator and I have one integration in the loop, it means that I can do first order noise shaping if I oversample the structure. And so that's an extra benefit, that by oversampling this structure, by reading out the phase detector signal at a frequency that is higher than the bandwidth, I can exploit this first order noise shaping, all with a highly digital structure. So the more I can do, I am using this oversampling, the more I can reduce my quantization noise, and therefore the higher my signal to noise ratio can be. So that's what I plot here. I plot the signal to noise ratio for different amounts of oversampling. So the different colors, dark blue, light blue, green, red, and black, correspond to different amounts of oversampling of the phase detector output compared to the bandwidth of the signal. And obviously, the more I oversample, so the more you go from dark blue to black, the higher your signal to noise ratio becomes. Then, of course, the question is there no limit to the signal to noise ratio? Well, of course, there is a limit, and the limit comes from the noise. But because we have an oscillator signal, the noise in this case is the phase noise or the jitter of the oscillator. And that's what you see on the x-axis. The horizontal axis is the amount of phase noise. So here, this means a lot of phase noise. This means little phase noise. And so with little phase noise, you see that indeed you can achieve very high signal to noise ratios, which decrease exactly proportional to the amount of phase noise. And only when you have not enough oversampling, then at these levels here, you are limited by the quantization noise and not by the phase noise. So ultimately, quantization noise can be resolved with sufficient oversampling, and that gives you a limit that is caused by the phase noise or the jitter of the oscillators. We then have demonstrated this principle of using analog functions, but not using analog circuits. There's not a single amplifier in this whole structure. There's not a single comparator in this whole structure. Everything is entirely digital. And we have demonstrated this concept for the capacitive readout, as I explained before. And so you see here the chip photograph that was done in a 28 nanometer technology, actually from ST Microelectronics in Krol, near Grenoble. And the important conclusion is here that, first of all, the area of this solution was extremely small, 0.0045 square millimeters. And small area means low cost. And secondly, we can operate these circuits at a voltage that can be as low as long as you can operate the digital circuits. And so the lowest level where you can operate digital circuits decently is 0.5, 0.6 volt. And so that's where we can reduce the power, the supply voltage, and therefore the power consumption. In the same way, we have built a time-based readout, not for a capacitive sensor, but for a resistive sensor. In this case, we put the resistors that we want to measure in a kind of Wheatstone bridge configuration. And so these are the two sensors that we measure. They are differential sensors in this example. And we put them in a bridge configuration with other resistors which are digitally controlled. And again, they are digitally controlled by the output of the circuit, which comes from a phase detector that reads the output phase of two VCOs, two oscillators, one controlled by this node and another VCO that is controlled by this node. And again, the loop tries to make the inputs equal. And so the loop will make the two oscillators run at the same frequency, which can only happen when this node and that node become equal. And when that is the case, then this digital output corresponds to the sensor signal controlling these resistors. You see again the chip microphotograph there on the right. And the same conclusion here is that this can be done in a very small area and is technology scalable. We then also did experiments to further improve the power consumption. And this can be done, for instance, by using a technology that is not CMOS, but another technology that has an energy delay product that is a lot better than CMOS. Remember that we are using digital circuits only, inverters, phase detector, and so on. They're all digital. Therefore, if we have a technology where the energy delay product is better, then this improves on the power consumption. The technology that we explored was a carbon nanotube technology, CNT. And why CNT? Because it has an energy delay product that can be 10 times better than CMOS. And a CNT transistor consists of a bunch of carbon nanotubes. And a carbon nanotube is kind of a folded cylinder consisting of carbon. And so we put a few of these in parallel. These are the yellow cylinders. We add a source, we add a drain, and then we put on top a gate. And depending on the voltage that we apply to the gate, either the transistor is turned on or is turned off. So it can act as a switch, and therefore we can build digital circuits with this. The technology that we used was technology that was developed at Stanford University. So it was a collaboration between our university and the University of Stanford. And we built a couple of circuits for reading out these sensors in carbon nanotube technology. An example is shown here. Again, it's a ring oscillator, so it's nothing else than inverters. So you see here. And we put these in a ring, and then we have a phase detector, and we read it out, and so on. Now, the interesting thing here is that in this case, we did not even need a sensor. Because one advantage of using carbon nanotube transistors is that the carbon nanotube transistors themselves can be functionalized to serve as a sensor. So the CNT transistors, which are the readout circuit, can themselves become the sensor if functionalized. And the functionality that we used was the fact that they are sensitive to infrared light. So that means that if you shine infrared light on a CNT transistor, then its characteristics change. Therefore, the delay in the ring oscillator changes. Therefore, the frequency of oscillation changes. Therefore, we can read that out in a digital way. And that is what you see here. where we were reading out the oscillation signal in darkness, and when applying infrared light, you see that the frequency changes, and it's this change in frequency that we digitize. We applied this to a CNT technology of 32 nanometer in microwatt. Here we are down to 130 nanowatt. So that's quite a huge reduction of the power supply, of the power consumption. So if I summarize this part, how can we achieve ultra miniaturization? Well, the suggestion I make is that we try to avoid using traditional analog circuits to implement analog functions, but to try to implement analog functions by using digital circuits where possible. Of course, we can exploit time, we can exploit oversampling, averaging, and so on, because of these technologies being so fast. And the use of advanced technologies like CNT technology and 3D stacking can also help. And of course, there is also the possibility to exploit the system level, meaning that sometimes it might not be needed to make every sensor on its own very accurate, but to build a system with a large number of sensors, which all of them are not so accurate, but where the combination of the information from all the sensors together at system level might result in an accurate measurement. Okay. A second question then is, how can we make such circuits robust? Are they not sensitive? Well, I just take the example of the resistive sensor readout. And we have to look at all possible errors that could occur, such as mismatch between the two oscillators, any changes in temperature, any variations in supply, and so on. And we found that by adding to the sensor readout two techniques, that we can address most of these problems. And so the first technique is the chopping. Now, I assume that you all know what is a chopping amplifier. When you're reading out something with an amplifier, you can chop at the input and at the output of the amplifier in order to get rid of any offset that the amplifier may have. Well, the same we can do here. The mismatch between the two creates an offset, for instance, an offset in the oscillation frequency. So by chopping at the input, and the chopping is indicated here by the crosses, the boxes with the crosses, at the output of the two oscillators and at the input of the two oscillators, we can achieve the same effect, that the impact of mismatch is eliminated. Now, since we do not work in the voltage domain, the chopping here in this case is in the time domain. So it means alternating, switching the two oscillator inputs and outputs. Okay, that is one technique. And the other technique is that we do a tuning of one of the oscillators. We can make one of the stages of the oscillators tunable, and then we can tune them to be equal to the other oscillator, for instance, in oscillation frequency for the same input. And we don't need a very accurate input. Any input is okay as long as it's the same for the two configurations. And so if we combine the two principles, chopping and tuning, then you can see here from the measured, so these are the measured results of this time-based chip that we developed now 2 years ago, 2-3 years ago, that in yellow you see the measured results that we have with chopping and with tuning, and you see that they are, you barely see the yellow, which means that it's buried underneath the two other measurement characteristics, and so the other measurement characteristics are much worse than the yellow one, which has the best performance. And in this way, we were able to achieve 15 bits effective for this readout. And as I told you, later on, we have been able to get even to 16.1 bits of readout. Now, this is for an automotive application, and therefore the technology that we use is still an older technology of 180 nanometer, but this is because they use high voltages in this technology. In an automotive application, it's also important that the chips operate from minus 40 degrees, so very cold, freezing temperature, to plus 175 degrees. It's never that this is the outside temperature, but this will be the temperature of the engine of the car. And if the electronics is close to the engine, it will have the same kind of temperature. And you see here that, again, using these techniques of chopping and tuning, that we can reduce the sensitivity with respect to temperature, that we can reduce it almost zero. So it means that the circuit performance does not change over this entire range of minus 40 to plus 175 degrees. So the change in performance is quite low. So that shows that we can make circuits small by using digital solutions. And B, in the last few slides, I showed that we can also make these circuits robust. So that means that we can use them in a car application or in a biomedical application without any problems in that respect. And that only brings me to the very last part, is how to make these circuits now smart. Well, what does mean smartness? Smartness means that we do not just use the sensor interface to collect data and to send the data, to transmit the data to a central server, because that would be just a dumb device. It would just collect data and transmit, and collect and transmit, collect, transmit. That would create a lot of data traffic, and therefore would consume a lot of power. Smartness or intelligence means that there is local processing done on the data. And so a couple of techniques I'm showing here is that how we can do local processing on those data in order to reduce the power that is consumed, so the total energy for a certain application, but also so not only for the energy, but also to maybe create from the processed signals, create some local information that could be used in order to steer the stimulation part of your solution, for instance, in a biomedical application. So how can we reduce the data? Well, one way is to use the technique called compressed sensing. So if we look at the signal of the heartbeat, so this is your heartbeat signal, a very well-known signal, then there is actually the information that we have in here is actually not in every instantaneous moment of the signal. The information that is relevant from a medical point of view is whether the shape is what it should be. So whether you have the big R peak and then followed by the two minor peaks and then the big R peak again, and what is the repetition rate of all these, that's the information, not the full sampled waveform. So if that is the only thing that is important for your application, then maybe there are mathematical techniques how we can reduce the original data mathematically to a lower amount of data that has, from a medical point of view, all the information that is needed. And that's what is done with compressed sensing. It's reduction of the data to a smaller set, but without losing information. And in this case, it has been shown that with only 8% of the original data, you can, on the receive side, reconstruct the signal without any loss of information. Now, if you only need 8%, it means that you save a lot in power consumption. So that is one technique, mathematical processing of the signals. A second technique is that we can have the processing of the signals being signal dependent. For instance, if you take the brain signal in this case, this is the spikes coming from the neurons, and this is the background noise, which we call the low field potentials that you measure. But it's like a noisy background. It does not contain any information. It's only when you have spikes that there is information. Therefore, we can use a quantization approach that is not linear. Whenever the signal is here, we do not need to know the signal with high accuracy because this background signal that is not so relevant. But it's only when there are spikes that we need to have the signal with a high precision. And so we can increase the resolution when the amplitude of the signal is high, and we can reduce the resolution when the amplitude of the signal is low. And so instead of using an A to D converter that has this staircase characteristic with average slope as shown here, we could make it nonlinear, having a slope like this, where we have a higher resolution at higher amplitudes. And so this was demonstrated here in a fully programmable chip, where the type of nonlinearity of the chip could even be programmed through the D to A converter that you see there, in order to build a signal-dependent processing readout. And a last thing is the event-based sensing. Again, in this neural application, in this period, there is no spike. So there is no information in this period. And only when there is a spike, there is information. So you may also think of putting the system to sleep or to a low power mode in this period, and then wake it up and process this with full capabilities, then put it back to sleep, and so on. So that is what we call event-based sensing. We only do processing, full processing, when there is a true event, and in the meantime we go in a kind of low power sleepy mode. Yeah. And so in this way, again, by turning the system off during large parts of the signal, we can gain in overall power consumption. Last part is, okay, we do this local processing. We can save power by only processing when there are events, or by making the processing amplitude dependent. The outcome is still data. Now, the ultimate level of intelligence that you can add to a sensing node is that you not only generate compressed data and transmit the data, but that you also interpret the data. And that means that you need to have some kind of interpretation circuit. And typically today for that, we use a neural network to interpret the data locally in the sensor unit. So we call that processing in the edge. And an example, just for illustration, is here, where you have a camera where you read out the image, but where locally in the sensor already, the image is not a set of pixels, but the image is converted into objects, and that these objects are converted into classified into type of objects. For instance, in the image you can classify, like, I see a car here, I see a second car, on the right I see 3 pedestrians, then there is a trailer somewhere, and so on. And this processing is done locally in the camera, and this can be used then in the context of autonomous vehicles. At this moment we are having a project in this sense, to build an autonomously flying drone. So not a a telecontrolled drone, but an autonomously flying drone that automatically recognizes when there is some object, when there is a house, when there is a tree, when there is a person, in order not to hit these things when it's flying through the air. And this we can then use to deliver, for instance, orders, pizza orders, and so on, to deliver them to your place, rather than having them delivered by these delivery boys or girls on their bikes. Okay, this brings me to the end of my presentation. Electronics has become ubiquitous, and in particular, in recent years, all kind of sensing applications with network sensing has become ubiquitous in what we call the Internet of Things. But it can also be used in the personalized medicine. It can also be used in autonomous driving and so on. And these are key drivers for the market of electronics today. In all these applications where there is interaction with the physical world, we need miniaturized sensor interfaces. And there I told you that as long as we design the analog circuits in a traditional way, they will not get much smaller. They will not. So if we really want to make them smaller, we have to do it differently. And so the possibility that I presented is that we build them with digital circuits, which then result in a small area and which also results in a scalable solution, scalable with improvements in the CMOS technology. In our case, this is then time-based signal processing. So the conclusion here is that I advocate to design analog functions, but without analog circuits. I also showed that reliability is key in many of these applications, and I showed some tricks, techniques to make the circuits insensitive to all kind of errors, mismatch errors, temperature variations, power variations, and so on. And then finally, there is the need for intelligent computing in the edge, which means that we need to embed. So that is not just a matter of data generation, but that we need to embed local information processing and even interpretation of the data in the edge, and in the future even with some learning capability. So that, take the example of the drone, that even when today it still hits the wall, that it learns by itself, so that next time it does not hit the wall anymore. So that brings me to the very end, and of course, all the results I presented, I did not make them myself. So I have to thank all my PhD researchers for their contributions to this work that I reported, and I have to thank the collaborators and the funding organizations to support the work. And if you have more questions, or you want to ask more things later on, you can always contact me at gielen@kleuven.be. Quite easy.
And okay, thank you very much. It was really interesting, really complete, and really clear. It was really clear, really complete. Do you have any question in the audience? Okay. Maybe I have one. During your when you design your oscillator and your ring oscillator, do you have, because of the loop, you have time constants and settling time problems during the digitalization of the data, during the voltage being digitalized and being coming frequency information. Do you have any delay and settling time problems during your design?
In principle, of course, you must satisfy those settling conditions, but the sensing applications, in most cases, they have a frequency range that goes up to 5 kilohertz, 10 kilohertz, 15 kilohertz at most. So it means that the signals that we are measuring have a very low frequency changes. That means that we have enough time for the choosing an oscillation frequency that is higher in frequency, maybe a megahertz, and then on top of that we do the oversampling of the phase detector readout, so that with digital circuits designed in a 180 nanometer technology, where we do an oscillation at megahertz frequency, is never a problem for settling.
Okay. Thank you very much. Yeah.
I have a quick question, but I'd like to thank you for your presentation, Professor. It was interesting. I'd like to know if your way to create a function is suitable for satellites application. If you need, if you talk about the reliability of electronics, I think it's friendly in a way of satellites application, and if you can implement it in satellites, for example.
Yeah. So a lot of this work was done because the example is an automotive application. So a lot of the work was done together with a company that develops automotive chips. So that means integrated circuits for a car industry. It was not with the satellite industry or the avionics industry, but car industry. And so they have very similar requirements, that the reliability of your car must be very high. Although a plane is even one step further, and a satellite, I mean, because you cannot just replace parts easily. But anyway, we did the project, and the first question they had was, can you demonstrate that you can have a solution that is cheaper? Cost. And so we came up with this idea. Okay, what determines the cost? The cost in the chip is determined by the area. Why can't we make the area of an analog circuit smaller? Because it's the noise and the mismatch. And so in the end we said, okay, let's go for time-based. And then indeed we were able to show that the area could be smaller. Then we reported that to the company, and the company came back and they said, okay, but now you show you can get to the same performance, but is not equally reliable. So we did a second project, and then we demonstrated that with the techniques that I presented, the reliability or the robustness of the solutions that we present are of the same level as the robustness of the solutions they use today. I'm not saying that in terms of robustness that they are better. I'm just saying they are similar, of the same level as what they use today. So that shows that the solution that we presented that result in a lower cost are equally robust than today's solutions.
Okay. Yeah. Thank you very much.
So that also means that you could use it in a satellite, for instance.
You're right.
Yeah.
Indeed.
Now, in all these applications, if you do sensing readout, there's always one calibration step needed.
Yeah.
Because, like I say, if you use a pressure sensor, you have a readout. At some moment in time, you need to have a well-known pressure. Look at the readout and say, okay, this readout corresponds to this pressure. So that single step calibration is always needed. So, but that is needed for every sensor that you have in your car. So doing that step for your satellite is also not a problem. Before you launch it, you better do that.
Yeah. Oh, yeah. Right. Thank you very much, Professor.
Thank you very much. Maybe another question. Thank you very much. It was a pleasure to have you virtually. We hope that we can be cool. We can be after welcome you at Bordeaux in person. Thank you very much for accepting the invitation. And, you are closing the week 21, and better for the last 2 years.
Okay, thank you again for the invitation. It was my pleasure. And I'll be happy to come to Bordeaux once, but like I said, you're all welcome to come to Leuven and maybe do an exchange with our student branch of IEEE. So
thank you very much.
Very much.
Okay.